Mr. Samuels here with a little lecture on quantum theory. But first, little review. Does light have mass? Of course not. It's not even Catholic. Okay. So, one of the important things to remember from our discussion of light is that the energy of a photon, which is the particles that make up light, is directly proportional to the frequency of light, meaning the higher the frequency, the higher the energy. So since violet light has a higher frequency, it has a higher energy than red light. That's why in photography, when they're developing film, they use red light because it has the lowest energy. So why do atoms only give off certain frequencies of light? If you look at page 367, you can get a good kind of picture of what's going on here. But the guy that figured this out was a guy by the name of Niels Bohr. Bohr's model, and on page 68 you can again see pictures that will help you understand a lot better. I recommend pausing the video and looking at the book at those figures there to kind of get an idea of what I'm talking about. He says that electrons don't exist in definite energy levels. They can't have any old energy they want. They have these specific energy levels, and as they jump between levels, energy is either absorbed or emitted. Since electrons are attracted to protons, moving them to a higher level means they have to absorb potential energy. And when they fall back down, that energy is released in the form of a photon. The higher the potential energy difference, the more energy lost, the higher the frequency of the photon. So that explains the different colors. All right, now the next important figure in quantum theory was a guy by the name of Louis de Broglie. You can pronounce him de Broglie if you really want to. But anyways, interesting guy. He was actually more of a political scientist, but he got really excited by the quantum revolution and started doing experiments of his own. He found that electrons exhibit that same wave-particle duality that Einstein proposed that photons had, meaning that electrons travel in waves just like photons do. They can bend around corners, they can diffract, refract, etc. And he thought that since confined waves only have certain frequencies, just like a different sized wine glass has a different note, that similarly, electrons could only have certain energies when confined in certain spaces in the atom. This explained the part of Bohr's model that said that electrons can only have specific energies. All right, the next figure in quantum theory that was important was a guy by the name of Werner Heisenberg. This is where Walter White from Breaking Bad got his famous name and the hat and the look for his character, Heisenberg. Heisenberg was doing detailed experiments on electrons, and what he found was something really weird. That the more he tried to measure the speed of the electron, his measurements on where the electron was were all wacky. So he thought maybe it was something wrong with the equipment or the experiment, so he redesigned new ones to try to pinpoint the position of the electron. But the more he did that, the more he found that it was impossible to find an accurate reading of the speed. He called this his uncertainty principle. It wasn't something wrong with the measurements of the experiment or the equipment. It's that electrons are weird. They can't really be pinpointed at one space at one time. So the guy that came along and made sense out of Heisenberg's uncertainty principle was a guy by the name of Erwin Schrödinger. And Schrödinger, he famously came up with his wave equation that described the movement of electrons around the atom. When you solve for Schrödinger's wave equation, you find out that you don't get one number in one place. Electrons don't exist in a certain place at a specific time, but in these regions of probability, places where they have a high chance of being found, called orbitals. Here's Schrödinger's wave equation. You'll have to have that memorized by next week. Ah, just kidding. Fooled you. No, actually, this would be if you studied something like chemistry or chemical engineering, maybe your third year of college, you might have to work with this using differential calculus. Okay, so let's try to understand what this all means. I'm going to play a little video here to just help you understand what electrons are really doing. Oops, is it not letting me?
A familiar depiction of the atom shows electrons orbiting the nucleus like planets around the sun. This model is neither accurate nor useful. We no longer think of electrons as orbiting the nucleus, and we cannot predict their location with accuracy. A more useful model is the quantum mechanical view of the atom, which represents the positions of electrons in terms of their probability of being in a particular region around the nucleus. If we could show all positions for an electron with a specific quantized energy, the resulting picture would look something like a cloud.
So the crazy thing is that's one electron. It's not moving around the nucleus in a nice, neat orbit like we thought before, like planets around the sun. But it's actually existing in all those places at the same time, kind of like a cloud. It's not really in one place at one time, but it's more in some places than others, and it's really strange. Unlike things in the big world, you'll have to use some imagination. It doesn't exist in one particular place until we look for it. I know that's a little strange, but that's just what the evidence shows. Even 100 years later, we still have the same results when we experiment with electrons. I really recommend going to my website and going to the notes. Go through the PowerPoint so you can watch this video again, or you can also find it in the videos link on my website as well. Okay, so the general idea that we're getting to is that that was just one electron. As we add more electrons, they fill more regions of space, more of these orbitals. And when we go on to our next topic, electron configuration, you'll see how that works. Thank you.